Well, hello and welcome again to our journey into number theory, and we're having a look at we finished up last time having a look at the outline of the general proof of Dirichlet's theorem, which I'll quickly remind you of. So the key steps in proving Dirichlet's theorem, that being that there are infinitely many primes congruent to B mod A whenever A and B are relatively prime. So the key steps were that L of S and chi has to be bounded away from 0 as S goes to 1 from above for each of the non-principal characters. This involves two steps, in fact. It involves proving that this sum is finite as S goes to 1, and also it's bounded away from 0 so I can take the logarithm of it. And that's quite hard. The next step, which we'll see is not quite so difficult, is to show that L of S and chi 1 diverges as S goes to 1. And then the final step is that for each B, we look at this sum, P congruent to B mod A, and we look at 1 over P to the S, and we write this as a linear combination of the logs of the L functions. And then we do this using orthogonality properties, and then as S goes to 1, because this one diverges and everything else is bounded, then that's going to show us that this sum diverges, and that means there are infinitely many primes congruent to B mod A. That is, there are infinitely many primes in the arithmetic progression B plus Ka. So to do all this, I went through this before, to do all this we need some basic results from complex function theory. So it's assumed that you've done at least one course in complex analysis and have some understanding of this. I'll remind you of the key facts. We're going to need the Vystras M test and uniform convergence. Now the Vystras M test says that if you've got a sequence A sub j of z, sequence of functions of a complex variable z, and if you can take the modulus of each of these and show it's bounded by some constant that'll depend on j but not z in some open set, and if you can also show that the sum of these mj's is finite, then Vystras M test tells us then that this sum, the sum of these complex functions, converges uniformly in this open set G. Furthermore, if each of these is analytic in G, and the series converges uniformly in G, then this represents an analytic function. So we're going to use the Vystras M test a number of times in what's coming up. I'll do a quick example of this just to demonstrate how it works for those who haven't done this for a little while. So here's just a very simple example. We're going to look at 1 over n squared plus z squared n equals 3 to infinity on the disk mod z between 1 and 2. So here's the example. And what we need to do, we need to get some sort of bound on the size of these functions here. So for n bigger or equal to 3, which it is at the moment because we're summing from 3, then the modulus of n squared plus z squared is bigger or equal to, well, its absolute value of n squared minus mod z squared. Now we don't need the absolute value because z is between 1 and 2 in modulus. So this then is bigger than n squared minus 4, and this is positive because n is bigger or equal to 3, and this in turn is bigger than, say, a half n squared for n bigger or equal to 3. So flipping this upside down, we get 1 over n squared plus z squared modulus. This is going to be less than n on 2n squared. So that's given me this is my m sub n's, and then if I take the infinite sum of these, then this of course is this is finite. It's just twice zeta of 2 minus a couple of terms at the beginning, so this is going to be finite. So that tells me by the Vystras M test, the given series converges uniformly on the annulus mod z between 1 and 2 to an analytic function. So this infinite series we start with is in fact does represent an analytic function on this annulus. So we now define a complex zeta function, which looks exactly the same as the zeta function we've been playing with, except now the s is now a complex variable. Now traditionally one writes s is sigma plus it. You'd expect sigma plus I tor might be more consistent, but historically people wrote sigma plus it and it's just stuck, so that's the way we write it here. So sigma and t are real. And then important factor, the modulus then of 1 over n to the s is just the modulus of e to the sigma plus it log n by definition. And the modulus of e to the it log n is 1, so we're just left with the e to the sigma log n, don't need absolute value signs there in fact, which is just 1 over n to the sigma. So important fact, modulus of 1 over n to the s is just 1 over n to the sigma, and 1 over n to the sigma, summing from 1 to infinity, is finite provided sigma is bigger than 1. So then that means by the Vystras M test, this new zeta function on any compact subset of the region sigma bigger than 1, this series converges uniformly, and this zeta of s defines an analytic function in the complex plane, provided sigma is bigger than 1, which can be differentiated term by term as often as we please. Now, the next key idea we're going to need is, and use quite a bit, is the idea of analytic continuation. And there are a couple of different versions of this. So if you've got two entire functions, f and g, that agree on some interval on the real axis, no matter how small, then f and g agree everywhere in the complex plane. This is a very, very powerful tool, a very useful tool. A simple example here, if you're trying to prove this complex identity, now z is complex, sine of the double angle formula, sine of 2z is 2 sine z cos z, you simply go back onto the real axis, and if I put x to be z to be x, which is real, then I get sine 2x and 2 sine x cos x, and we know that this is a true identity back in the real world. And so because these two functions here, the sine 2x and 2 sine x cos x, because they agree on the real axis, even on some part of the real axis is all we need, then the theorem tells us that these agree everywhere. And so it's a nice way of getting all of the complex trig identities you get immediately from all of the real trig identities. Same for hyperbolic identities. Second idea of analytic continuation is, I'm going to just do by example really firstly. This is one of my favourite examples of trying to get your head around analytic continuation. I start off with f of z is 1 plus z squared and so on. Now this is a geometric series and it converges uniformly in the open disk mod z less than 1, which you can show easily by using the ratio test, but not outside. Now, if we're inside the disk, mod z less than 1, then we can sum this series. It's just a geometric series, the modulus is less than 1, so we can sum it, and the formula gives us 1 on 1 minus z. If I now just give you 1 on 1 minus z and forget everything I just said a minute ago, then this function, g, is meromorphic, and it's got a simple pole that z is 1, and the residue is minus 1, fairly clearly. So, this function works everywhere except at 1, and for mod z less than 1, these two functions are equal. And so what we do is we say then that this g is the analytic continuation of f. So f only makes sense in this region. However, in this region it equals G, which makes sense everywhere except at 1. And so we say that this is the analytic continuation of F. Another way of thinking about it is to say we could redefine this F, which is only defined in one region. We could redefine this function to be this function, and this one is valid everywhere except at 1. So we say that G is the analytic continuation of F, and it's got a simple pole at Z as 1. So, more generally, given a function f, which is analytic in some domain D, then if, and that's a big if of course, then if there is a meromorphic function G, defined on some domain which contains D, and this function G agrees with f inside D, then we say that G is the analytic continuation of f. And what's more, if you've got such a G, then happily it is unique. Such a G, if it exists, is unique. So in this, chapter, in the next section, we're going to see how to analytically continue our new zeta function. At the moment, our zeta function represents an analytic function for sigma bigger than 1, and we're going to push the boundaries a bit and push it back to sigma bigger than 0 by showing there's an analytic continuation of the zeta function. In the next chapter, where we look at the Riemann zeta function in a bit more detail, we'll analytically continue zeta to the whole of the complex plane. So we're now going to embark on a proof of Dirichlet's theorem, which requires, again, a number of technical results. So firstly, we do the usual setup. This is exactly what we've been doing up till now, but now we're going to do it in a bit more generality. So here's the setup. We fix A, which is a positive integer greater than 1, once and for all. So I fix A from everything that's coming up from now on. We take a character, mapping ZA or UA if you like, into the complex numbers. We take that to be just an ordinary group character. And as above, we define the Dirichlet character, chi superscript 0, mapping the integers into the complex numbers for I equals 1 up to phi A. And of course we know that that's the number of characters we're going to have. And we do the usual thing. If n is not relatively prime to A, then chi sends it to 0. And if n is relatively prime to A, then we read n mod A, and we get n hat. And we simply map n to chi I of n hat, which is what we've been doing exactly up till now. And as usual, I'm going to just drop the superscript 0 there. So as before, we define the Dirichlet L function. L of s and chi is the sum chi n on into the s, as we've done before, but now we're going to take this s to be a complex variable whose real part is greater than 1. Now, by the Vystras M test, it's very easy to show that this converges absolutely and uniformly to an analytic function in this region. Because as soon as we take the modulus of this in here, the modulus of all the chi's is 1, and so it's the same argument we used before on the zeta function. So Vystras M shows that this is an analytic function, and again, without going all the gory detail, as we saw before, because chi is multiplicative, we can write the Dirichlet series as a generalized Euler product. The only difference, of course, here is that s is a complex variable. Now we need a technical result, a little tool called Arbel's summation formulae. And you may have come across this in your travels. This is sometimes called summation by parts. It's a little bit like integration by parts, but it's a version that's used for sums. Not quite as neat as the integration by parts, but nonetheless it's very similar to it and is very useful when you're trying to sum series that are the product of two sequences. So it says if you take this, you now firstly you take an and bn to be sequences of complex numbers. You put an to be the partial sums of the little a's, a1 up to an. And then for n bigger equal to 0, we're going to set a0 to be 0, by the way. And we take m less than capital N and bigger than 1, or equal to 1. Then when we sum this product, an bn, from little n as capital M to capital N, then we get this expression. So it's a little bit like integration by parts, where you normally integrate one term and differentiate the other. Here we're sort of, integration is like summation, so we're replacing the integration by summation, which is what this capital AN does. And then instead of taking a derivative, we're taking what's called a difference, so we're taking bn minus bn plus 1. So we end up with this sum, and we get a little bit of a few terms at the beginning and the end. So these are just coming from terms, the initial terms and end terms, and they turn out to have that shape there. Second part of the Arbel summation formula is to say, well, suppose the infinite series converges, and suppose also that an bn goes to 0 as n goes to infinity, that is the product of this partial sums times bn goes to 0. We know that little a and bn has to go to 0, but this is slightly stronger. We want the partial sums of the ans times bn to go to 0. Then this sum, this infinite sum, can be written as the sum n equals 1 to infinity of the partial sums of the little a's times this sort of difference on the b's. And before I do a proof of this, I thought I'd just do a quick example to show you how it works. This is not the most elegant way or the simplest way of summing this particular series. I'm sure you can come up with much better ones, but it's just an example of how this summation formula works. So we've got S as the sum n equals 1 to capital N of n times 2 to the n. So I'm going to choose the a sub n to be 2 to the n and my bn to be the n there. So capital A is the partial sums of the little a's, so I write that down, and that of course gives you a geometric series which I can sum easily. I'll leave you to check. That's what you get when you take the sum of this. You get 2 times 2 to the n minus 1. Now this funny difference bn minus bn plus 1 is just n minus n plus 1, which is minus 1. And so I plug these into the Arbel summation formula. So this sum then is, I get the bn, that's the difference, which is minus 1, I pulled out the front, and then I get the capital A sub n, and the sum now goes from 1 up to capital N minus 1. Plus, the next term was the capital A n, capital B n. So capital AN is this expression with little n replaced with capital N, and Bn was n, so we replace it with capital N. And because A0 is 0, capital A0 is 0, then that other term in the formula is just 0. Well, I've just split this up into 2 bits, copied down the last bit. This again is a geometric series, so I can sum that one very easily. This one we're adding up capital N minus 1 times, so I get this term and copy that down, and then I just simplify and I get 2 to the n plus 1 plus 2 after simplification. Now, as I said, this is probably not the most elegant way of summing the series, but it's just an example of how to use this Arbel's summation formula. So, quick proof of the Arbel summation formula, and I'm just going to do part B. Part A is done similarly. It's just a little bit more fiddly because of the endpoints. So I'm going to put capital SK as the partial sums of these firstly, from n equals 1 up to k of a n b n, and we set a0 to be 0. Then the sum of the first n little a's minus the sum of the first n minus 1 little a's gives us the last term, which is a sub n. So I'm just replacing little a sub n by this difference here. Split this up into 2 bits. Now I'm going to replace n minus 1 with n, and so I simply, in this sum, so I simply do a change of summation variable on this one, replacing n minus 1 with n. And so I leave you to check that's what you get, remembering that that capital A naught is naught, and so although when you change the dummy variable here, you start with little n as 0, because of A naught is naught, we can just sum from 1. I peel off the last term of this series, which is A sub k, B sub k. I do that so to make these top limits the same, and then I can pull these together in here and factor out the A sub n's. Now, one of the conditions of the second part of the Abel summation formula was that this thing goes to 0, so as k goes to infinity, that goes to 0, and this thing just ends up there, and that's the second part of the summation by parts formula. So I leave you to do part A and fiddle around to get all the constants correct. Now, what we're going to now do is we're going to show that this function sigma of s minus 1 on s minus 1 can be continued to an analytic function in the region s is complex number, where the real part of s now is bigger or equal to 0. So we know that sigma of s is analytic for real part of s bigger than 1, and now I'm going to take this and subtract off this term and analytically extend this then to a function which is analytic for a real part of s bigger than 0. Now, in fact, we'll see later, of course, that this term here, if you take this function zeta of s and you construct its Laurent series about s equals 1, then this, of course, turns out to be just the principal part. But we'll look at that again in the next chapter, but we're just going to show at the moment that this function can be continued to an analytic function on this region. And to do that, we're going to have to find a formula for this that is valid for a real part of s bigger than 0. And that's going to be given by Theorem 4.4. So that is going to tell us the real part of s is, we're going to take the real part of s bigger than 1 for the moment, and we're going to show that this zeta of s can be written as s over s minus 1 minus s times the integral from 1 to infinity of the fractional part of x over x to the s plus 1. So this symbol denotes the fractional part of s. And we'll have a look at the proof of that and continue on in the next video.